The next is going to be the catalyst. The catalyst by definition is actually any substance that alters the rate of chemical reaction and remains qualitatively and quantitatively unchanged at the end of the reaction. Such a thing is what we call a catalyst. Remember, don't say that catalysts are substances that speedens up the rate of chemical reaction. No, you are being one-sided and biased. You are defining only positive catalysts if you define like this. A catalyst will alter the rate of reaction. It will either slow it down or make it faster. And therefore, we correctly define catalyst as any substance that alters the rate of chemical reaction and remains qualitatively and quantitatively unchanged, meaning it will not affect the product. It doesn't take part actually in the reaction. It cannot start a reaction. Rather, it can only affect the speed of the reaction. It might slow it down, it might make it faster. And this implies that we have positive catalyst and negative catalyst. And there is nothing actually that we can single out and call catalyst in science. No. But most catalysts are found among the transition elements because they have variable oxidation states. So the elements in the transition group, that's in the D block in the periodic table, are usually catalysts, and their compounds are also catalysts, such as manganese 2 oxide, manganese 4, cobalt, nickel, platinum, iron, finely divided iron. These are the common catalysts we have. But apart from them, any other substance can also act as what? A catalyst. It is not a must, it must be the transition element, but they are the most common catalysts we use. So a catalyst in a given reaction can act as a reactant in another reaction. That is why we don't have one particular thing we refer to as catalyst. For example, manganese 4 oxide will speeden up the rate of decomposition of hydrogen peroxide to yield water and oxygen, but it will not affect the product. Therefore, in the decomposition of hydrogen peroxide, manganese 4 oxide is a catalyst. But in the production of chlorine from hydrochloric acid, manganese 4 oxide reacts with HCl no longer as a catalyst. That manganese 4 oxide there is there as now oxidizing agent. So that something is a catalyst in a given reaction doesn't mean it will remain to be a catalyst in all the reactions.
General characteristics of catalyst. 1. Catalyst remains unchanged. Both the chemical nature and the mass of the catalyst remains the same after catalysis, even though some physical properties such as the texture and color may change, but the chemical nature remains the same. Then secondly, catalysts will alter the rate of chemical reaction. Then thirdly, a catalyst cannot affect the equilibrium position of a reversible reaction. Note this. Rather, what can affect are the temperature, pressure, and concentration. They can affect. Then, a catalyst cannot start a reaction like I told you earlier. Then, the fifth point is that a catalyst cannot affect the nature of the product. Then, the effect of solid catalyst can be improved upon by increasing the surface area of such catalyst. Then, catalysts are specific in action. That is, a catalyst is only effective in specific reactions. That's why I said earlier that we don't have anything like a generalized catalyst. It will also be good if you know that enzymes are organic catalysts. Of course, that is when we talk about the digestive enzymes, they are also what? Catalysts. So now, remember that when catalysts and the reactions it is catalyzing are in the same phase, we call it homogeneous catalysis. That's when the catalyst is in solid and also when the reactants are also in solid, we call it homogeneous catalysis. But when the catalyst is in different state from the states of the reactants and the product, we call it heterogeneous catalysis. So let us see more about catalysts.
Wait a minute, have you heard about the Majestic Table? It was designed and recommended by Her Majesty himself. Here it is. The amazing thing about the Majestic Periodic Table is that it provides a clear and colorful classification of elements from P block metals to metalloids to liquid metals. It also shows the boiling and melting point of all the elements. It also has the unique feeling of electrons in the shells of each element.
enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this majestic periodic table, demand and special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that we have, there are like, some still see promentum has not been radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it majestic.
This is super majestic.
Much love.
So we have defined catalyst and given the proper introduction of a catalyst. And catalysts are usually written on top of the arrow of a given reaction. Meaning, if we have such reaction, if A plus B reacts to give you C plus D, and then E acts as a catalyst, the E is on top of the arrow, indicating that it is neither a product nor a reactant. So that's how we write it. Now, let's now bring you close to how catalyst alters the chemical kinetics. How does it alter the rate at which the particles are converted from reactant to product? Catalyst alters the activation energy of a given reaction. Catalyst alters the rates of a given reaction by affecting the activation energy, either by making it higher or lower, either by raising it or bringing it back. So taking you back to what I defined as activation energy, we need energy profile diagram to illustrate how catalyst affects the rate of chemical reaction. Okay, here we have such graph. This is for endothermic reaction, where here is 0, 2, 4, 6, 8, 10, 12, 14, eventually 16. So tracing this, see them, and tracing this. You have to label this to make it clearer for you. So from here, to here is what we call the activation energy. We call this the what? The activation energy. The activation energy, which is mathematically on top, is here, we call it the activation complex. Here is referred to as activation complex, which is the peak. And then mathematically, the activation energy is actually, here is our what? From here to here is the enthalpy of the reactant, where here is A plus B to give us C plus D. So over here is the heat of the what? The enthalpy of the reactant. The enthalpy, that's the heat content of the reactant particles. While over here is the heat content of the product particles. Here is the heat content of the product. So, for us to understand what activation energy means, activation energy, we say, is the energy barrier or the minimum amount of energy that must be supplied before the reactant particles are converted to product particles. And mathematically is the difference between the energy, is the difference between the activation complex and the enthalpy of the reactant. Enthalpy of the reactant, not enthalpy of the product. So the activation complex minus the energy of the reactant gives you activation energy. So activation energy is equal to, here the activation complex is what? 16 minus the enthalpy of the reactant, which is 6, such that our activation energy here becomes what? 10, usually in kilojoule per mole, whichever. So we have 10 kilojoule as our activation energy. Now, a given reaction, this particular reaction can only occur when you supply 10 kilojoules of energy. And such collisions of the particles that will supply such energy is what we call the effective collisions. Collisions that are enough to break the bonds holding the reactant particles. So 10 kilojoules must be supplied before A and B is converted to C plus D. If you supply 9 kilojoules, A and B remains what it is. There won't be any change or transformation, and therefore there won't be any chemical reaction. Now, what a catalyst will do for you is to either take this activation energy higher or lower, either to raise it or to bring it back. So I'm going to draw the energy profile for catalyzed reaction and uncatalyzed. There are two possibilities. Yeah. There are two possibilities. The two possibilities are the one raising it and the one lowering it. What matters is that this one on a full line, on a thick line, is the uncatalyzed, while this one is the what? Catalyzed. While here is still the what? Catalyzed. So catalyzed can come in form of the one taking the complex higher or lowering it. So this, what can only do this once on the dot is nothing but a catalyst. So a catalyst can affect the rate of chemical reaction either by taking the activation complex higher or lowering the activation complex. In the first case here, in case of the one I'm labeling X, this one is Y, while Z is uncatalyzed. That's the normal rate. Without catalyst, this is the way to proceed. But if you add catalyst, X is a positive catalyst because it lowers the activation energy by lowering the activation complex. While Y here is a negative catalyst because it increases the activation energy by increasing the activation complex. So if you take these traces, here will now become our 18 kilojoule, for example. So now, checking this, catalyst can affect the rate of reaction. We solved the uncatalyzed as 10 kilojoule. But if you apply a positive catalyst, the activation energy will now be, you trace it, because the complex will be lowered from 16 to 14, such that the activation energy will now be, for the catalyzed, positively catalyzed reaction, is going to give us exactly what? 14 minus the heat content of the reactant remains 6, is unchanging. It doesn't change. So what we have here now is 14 minus 6. And 14 minus 6 will give us 8, if I'm correct. Yeah, this is going to give us 8 on the dot. So you see that if you are told to supply, to push a mass of 10 kg and push a mass of 8 kg, for example, you will know that you spend less energy in pushing this, and this job will be easier done. And what made it easier for you? The catalyst lowered it from becoming 10 to becoming what? 8. And that is what catalyst does for positive catalyst. Then for negative catalyst, what happened here is that it raised it from the 16 to 18. So the energy, the activation energy of the same catalyzed will still be, but this time around is negative catalysis. That is, this Y is used when you don't want this reaction to proceed. So negative catalysts are mostly used as preservatives to inhibit and stop some reactions or slow it down and then keep the quality of that product as it progresses. So in most preservatives, you are advised to use a negative catalyst to stop the undesirable reactions. So in this case, you are making the activation energy higher. The catalyzed, we have catalyzed for X and catalyzed for Y. Catalyzed for X here is 8 kg. Then catalyzed for Y will now be 18 minus 6, which will be 12 kg. This one, you are making the job harder for the person. If you are told to push 10 kg and you are finding it a bit difficult, when the mass increases to actually 12 kg, that makes it more difficult for you. So negative catalyst slows down the rate of reaction, while positive catalyst increases the rate of reaction. But all the same, whether negative or positive, both affects the rate of what? Reaction. So the catalyst as a factor affecting the rate of reaction has been explained very, very well. To use the opportunity, I teach you what exam body might ask you. They will ask you, what's the energy change of the catalyzed? You see how I solved it here. If they drew X for you, you solve it this way. What is the energy for the uncatalyzed? You solve it this way, which is 10 kg. They might not ask you, they might label here, X. Label here. If they tell you X here, you tell them the heat content of the what? Reactant. Then another remarkable thing that we need to note is this: the difference between the energy of the product and the energy of the reactant, and that is what we call enthalpy change, heat change, which is heat of product minus heat of reactant. Considering this energy profile diagram, C plus D, the energy content of C plus D here is 10, while the energy content of A plus B here is 6, which means the energy of the reactant is less than the energy of the product. And if this happens, the reaction becomes endothermic. So in that case, this is H equal to 10 minus 6, which will give you automatically 4, and is a positive number. The opposite is the case. So the energy profile diagram I showed here is for endothermic reaction. That is, it means that extra energy, extra 4 kilojoules of energy is absorbed from the surrounding, which makes the reaction vessel to feel colder to touch, because the reactant takes in that heat from the surrounding to produce the product, because the energy content is 10 while the energy started from 6. Therefore, there have to be absorption of extra 4 kilojoules. But what if I twist it this way? Yes. The reverse reaction of this will be automatically the exothermic, the energy profile diagram for exothermic, where here is now 10. We keep the 10 constant. Then going down, giving us now 6. Here becomes, if you have such reaction, if we keep the labeling A plus B and keep C plus D again, it means that the heat change is still the difference between the energy of the product and the energy of the reactant. So here is your heat change, while from here to here is your activation energy. Remember, from here to here it doesn't signify anything. The difference between the activation complex and the energy of the product doesn't signify anything at all. So take note, please. This one is nothing. It's always the difference between the activation complex and the energy of the product. Now, heat change here to show is this is an exothermic reaction. This is exothermic reaction, while this here is endothermic. Whether exo or endo, what I taught you about catalyzed and not catalyzed remains the same. But what's the difference is just the heat change. So heat change here should be, this is the HP, heat content of the product, because C plus D now is 6, minus heat content of the reactant, which is 10. This time around, the heat change is negative 4 minus 4, which means 4 kilojoules of energy have to be liberated, has to be lost in the surrounding, and that's why the reaction vessel is hot to touch in exothermic reactions. So exothermic reactions, the ones that liberate heat, and heat change is usually what? Negative. But if they draw the same thing here, this is for catalyzed. Then another one, usually in dotted line, this is also for catalyzed.